Hi, in this video, we want to take a look at measures of dependence for time series. All right, so we're going to be working through some examples from time series analysis and applications. Here are the authors, and here is their GitHub page. And you can download the GitHub package through this code here. I have it commented out. All right, so let's go ahead and dig in. Let's take a look at what we've got going on. All right, so first thing I'm going to do, just like I always do in any project, I make sure I have my workspace set up the way I want it. So here I am limiting output to 3 significant digits. And here this is saying that I want to avoid scientific notation if I can. And this is just removing anything that's on my workspace when I run my code. Make sure you're aware of that before you run my stuff. All right, so we're talking about time series. So if I have in particular points of time that we're interested for the same time series, one way to tackle it would be to look at the multidimensional cumulative distribution for all n states, for all n points of time. All right, so I could do that. So take the n points of time that I'm interested in for the time series, and then take a look at the distribution function that we have. So remember that when we're taking this approach with the probabilities, the multi-dimensional cumulative distribution functions, we're checking to see the probability of being less than or equal to each of these particular values. Now, very quickly, this will not be feasible for humans to interpret. Maybe 3, you could work out some inference. 2, you could probably do something, but really this is too much for us to work for. So instead of working with a whole kit and caboodle, what we're going to do, we're going to work with something that's easier for humans to interpret, and we're just going to look at one dimension at a time, or one point of time along our time series, and we'll take a look at the probability that our time series at a given time will be less than or equal to a particular value. And we'll call this capital F sub t as the function. And very naturally, if I take the derivative, assuming that it exists, it doesn't have to, here we can get our density function very nicely. All right, so let's go ahead and take a look at an example. So let's say that each moment of time along my time series is Gaussian with mean mu sub t, sigma squared sub t. All right, now something about this is that if you look at this, that's considered a constant with respect to time. This could actually vary across time, but once I have a hard fixed time component, I know the t, it's considered a fixed parameter value for this. And we'll abbreviate this as x sub t. The time series is normally distributed with a mean and a variance at that particular point in time. And here is the standard bell curve function. All right, well, just like in the rest of statistics, we're going to have the mean. And so the mean will be defined exactly how we would expect it to be. That I'm going to take the integral of the variable times the density function, integrate over the entire possible value, all possible values. Now, if it's discrete, then I'll be doing the summation. And assuming that this is finite, assuming that it is defined, that we will get our expected value. And we will denote that with mu, just like in the rest of statistics. And so this only applies when the expected value exists. And notice that the expected value of our time series is actually a function on time itself. So something that will happen as you work through this is sometimes time will be treated as a constant, sometimes time will be treated as a variable. It depends on the context of what you're working on in that moment. All right, so let's take a look at the mean function of a moving average series. All right, so we're going to go ahead and say that we're working with a white noise series. And we're going to say that we have expected value of 0 for all points in time. All right. Well, you know what I could do? I could do a smoothing series for this. And during this past week, actually yesterday, I did a smoothing series similar to this. It's a little bit more complicated because over months for the problem I was working on. But what we're doing here is I'm taking consecutive points of time and I'm averaging them out. And the problem I was working on, I was taking the average of 3 months at a time because quarters were important for this particular project. And so similar to this, I took 3 points of time and then I took the average. And when I applied that compared to the original time series, it was a lot smoother. And it was easier to see what is like the average of what's going on. All right, well, if this is my smooth time series, one thing that'd be very natural to ask is, what's my expected value? All right, well, what we could do, I could just take the expected value of v sub t, and then the expected value is a linear function. So I take the expected value of this fraction, slap it into e parentheses, use the linear aspect, and then I see that I have the expected value of each of my w sub t's, which I know are each equal to 0. Therefore, the overall expected value is equal to 0. Easy peasy, lemon squeezy. All right, let's do this again, but this time, let's take the mean of a random walk with drift. All right, once again, we're going to use the white noise example, but this time, for my white noise, I'm going to say that it's a random walk. So at each point of time, there is a random variable that is, my white noise and has expected value of 0. And what's happening is that wherever I'm at, I'm going to add a drift aspect of delta plus that random variable aspect. And this is going to be my random walk. So this would look more, for most cases, it'll look like it's kind of jagged up and down, up and down, up and down. All right. And so here, if I go through and I want to take the expected value of my time series, I just drop that into E of my time series, expected value. So now I take this, slap it in for this. I use the fact that the expected value is once again a linear operation. This is going to be treated as a constant. There's no randomness to it. So the expected value of delta of t is just delta of t. And then the expected value of a sum is the sum of the expected values. Boom, we get this portion. And this we know is equal to 0. So we know that that is our expected value. And so if I was to plot this, as time went on, what would happen is there would be the drift component, and my random walk would be going up and down, up and down, up and down, but it would keep hovering somewhat close to the delta of t function. All right, now let's consider the situation where I have a sine wave. We're going to use cosine in this example, but let's say I have a sine wave, and there is a signal from the sine wave plus some noise. And so here is my noise component. Here is my sine wave. And then I'm writing 2 pi just to make things easier to interpret. If you've done Fourier analysis, it'll be obvious to you why you do this. Or, the amplitude is here. And we have our amplitude, phase shift, all that beautiful stuff. All right, so now I'm going to take the expected value. So I'm going to drop this whole thing in. So when I compute the expected value of my time series, I take the expected value of the whole thing. Well, you'll notice that this is not random. That is constant with respect to time. So once I know what time is, it's a fixed value. And so this is a constant value for the purpose of expected value. And so this is, this is our random aspect. I'll break up using the linear function, and then I'll take the expected value here, which is equal to 0. Boom, we see that the expected value is the signal itself. All right, that's good. All right, so that tells us about expected value. Now we want to take a look at the relationship between different points of time of the time series. So we're going to look at autocorrelation. So the reason why we call it autocovariance, autocorrelation, means that it's a time series covariance with itself. Autocovariance is the covariance of a time series with itself. Autocorrelation is the correlation of a time series with itself. All right, so what we're going to do, we're going to define this function where I have gamma of my time series. I specify the times, and that's going to be the covariance of the time series at the two different points of time. And covariance, standard definition, is going to be the random variable minus its expected value. Random variable minus its expected value. Take the expected value. All right. Basically, just an extension of regular old covariance from our other statistics courses. Now, as we talk through these expected values, variance, covariance, correlations, we're making the assumptions that things are finite when they need to be. If it's not finite, then as I'm working through, let's say I don't have finite variance, I'm doing something that requires finite variance, we just say it's undefined, it doesn't work out. So as we work through all these definitions, if there's a special case that doesn't make sense, the definition doesn't apply. All right, so autocovariance measures the linear dependence between 2 points of time, 2 points on the same time series observed at different times. All right, so very smooth series exhibit autocovariance functions that stay large even when S and T are far apart. And choppy series tend to have autocovariance functions that are nearly zero for large separations. All right, so now recall from your regular classic statistics class that the covariance or correlation is equal to 0, then the two variables are not linearly related, but there could still be some dependence structure between them. All right, so here, when I see the autocovariance or autocorrelation equal to 0, I know there's not a linear relationship between them. That doesn't mean they're independent. So I'm going to show you an example where they're not independent. All right, so let's go ahead and say that I have an X, I have a Y value, and from this X and this Y, if I take the covariance, you can see that within machine accuracy, that's equal to 0. And the correlation is equal to 0. All right, now let's look at the actual plot. We can see that the plot forms a perfect circle. All right, so if I knew what the X value was, and I know it's on a perfect circle, I know that the Y value is one of two possibilities. This means that we do not have independence, even though we have perfect 0 covariance and correlation between them. So 0 covariance, 0 correlation means we do not have a linear relationship, but we could have a more interesting, more exotic relationship going on. It's harder, that could be harder to spot. All right, now there is a special situation. When I'm dealing with normal, multivariate normal, 0 correlation does mean independence for us. So if I have multivariate normal and 0 covariance, 0 correlation, then we have, in fact, independence. But we have to have that normality be true. Otherwise, it doesn't make sense. Now, if I look at my covariance and I look at the situation where I'm looking at both points in time are the same, then this will be, in fact, the variance of my time series at that particular time. Okay. So now let's take a look at the autocorrelation of white noise. All right, well, if we have a white noise time series with expected value of 0 for all points of time, then my covariance will be equal to 0 if I'm looking at two distinct points in time, but I'll get my variance of the time series if the 2 points in time are the same. All right. Now, let's go ahead and take a look at linear combinations of random variables and the covariances that we can get from them. So let's go ahead and say that I have any two random variables that are linear combinations of some other random variables, x and y. All right, so we're going to say that u is a linear combination of the x random variables. So the x random variables are random variables. The a's are coefficients, and then u is the coefficients times the random variables added up. V is going to be defined similarly. I'm going to take a bunch of random variables, y, multiply them by constant coefficients, add them up. That is my v. Then the covariance between u and v is going to be the sum of the covariances between x and y times the appropriate coefficients. And then, in fact, very naturally, the variance of u is going to be the covariance of u with itself, and the variance of v is going to be the covariance of v with itself. All right. Let's take a look at the autocovariance of a moving average. So once again, I'm going to take a time series. I'm going to average over 3 points. And here we're going to be using our white noise series, time series, in the previous example. And so my covariance of my smooth time series at time s and times t, well, that's just going to be, I'm just replacing v sub s with its definition and v sub t with its definition. All right, well, first we're going to look at the situation where s is equal to t. Then I see that I have the same thing twice, so I know it's going to be a variance calculation. Now, if I go through and I do the full formula that we just looked at, if I take advantage of this formula, what's going to end up happening when I do the cross multiplication, whenever these guys have different subscripts, it's going to be a covariance of 0 from the property that we looked at a moment ago, because it's white noise. All right, so whenever the subscripts do not equal each other, I know I have a covariance of 0. And then I have all the other cases where the subscripts are equal to each other. All right, so when they're equal to each other, well, I go ahead and drop this. I've got these 3 cases. Now, this 1/9 comes from multiplying by the coefficient for here and multiplying by the coefficient here. All right, and so now I know that I have constant variance of the situation. So then I replace each of these covariances with the variance of the time series, and boom, I get it. Now, when we look at the case where s is equal to t plus 1, we're going to play the same game. I'm going to go through and I'm going to take all the different covariances of the different subscript time series. And I'm going to be multiplying by the coefficient, just like I did before. Now, something that's important in this calculation that isn't really apparent here is something that happens that every single time that the subscripts are different, I have a covariance of 0, and those just get dropped out from the calculation. So what happens is the only time that the white noise time series gets included in the covariance calculation of not being 0 is when the subscripts match up. See, I got TT and I have T plus 1, T plus 1. And then I do my calculation, boom, I've got it. All right, and so we can do this again, and we get all possibilities to work out. Now, at a certain point, if I have enough separation between times for my smooth time series, then there's not going to be any overlap in the subscripts. When that happens, the covariance is going to be equal to 0. All right, so when I take 2 points of time for my smooth series, if they're far enough apart, I'm going to have a covariance of 0. Now, when they're closer together, the covariance is going to depend on how many of those subscripts are matching up in that average of 3 that I've got going on. And so we can see that when S is equal to T, we have the largest covariance here. And it gets smaller as S and T get farther away from each other until we get 0. Now, something that's interesting about this is that the covariance depends on the separation between times. All right, so the more of a lag of time that I have, the smaller the covariance is. The covariance depends on the separation, but not the location in time. If, S is 5 minutes and T is 6, that gives me the same as 10 and 11. It doesn't matter when we look at the covariance. It's a question of how far apart are the two times of interest. All right, so the smoothing time series by using moving averages gives a covariance that decreases with the separation of time. The covariance function depends only on the time separation, that is the lag, but not on the location of the points in the time series. And so we're looking at this as being weakly stationary. So the mean does not vary with time. Autocovariance does not vary with time, but location, it depends on location. It does not depend on location, but it can depend on difference. And variance is finite. Now let's look at the autocovariance of a random walk. Okay, so here we're going to take a bunch of uncorrelated random variables. And, so we'll say that we have 0 covariance. And I'm going to make a random walk of adding up the first few observations of the random variable. So I have a random variable by itself, and then I'm going to go through, I'm going to add up that random variable for the first T times. And the addition of the first T observations of it will be my time series up to time T. Now, what we're interested in is what is the covariance on the random walk, not on the original random variable, on the random walk. All right, well, what we're going to do is I'm going to take a look at this covariance, and just to make things easier, I'm going to set it up, I'm going to make the assumption that the first one is the smaller one, just set it up like this. All right, so we have two different ones, S and T. One is bigger than the other, or greater than or equal to the other. And let's go ahead and use the fact that covariance of A with B is the same as the covariance of B with A, so I could switch the order in my covariance function without messing anything up. And so here, let's say that this one is the minimum, and the one that's over here is the maximum. And I should have a +1 right here. Should be a +1 right there. All right, and so now I'm going to use the formula that we had for breaking up the things into covariance. And so now I've got this time series. I've got two separate time series here. I'm going to break it up into two components for the covariance. And it's going to work out that here, this is going to have covariance of 0. And this should be a T plus, or this should have a min +1 right there. That has an error. And then if I sit down, I work through this, I'm going to see that, in fact, I'm going to go through, I'm going to expand out that formula that we had previously for the covariances. And once again, it's going to be every single time that the subscripts match, I'm going to have a non-zero covariance. Every time that the subscripts do not match in the computation of this part here, I'm going to end up getting 0. And so how many times do they match up? Well, it's going to be the minimum of S and T. So now something that's interesting about this one is that the autocovariance depends on the time that we are looking at the minimum of the 2 times that are of interest, but does not depend on the separation or the lag. So it's going the other way from the previous example. Now, something to notice is that the variance is going to increase without bounds as t increases. All right, and just to kind of show you an example of this, here's some code. So I'm using random number generation. So I'm using set seed. Here's the number of observations that we'll have in a time series. Here's the number of time series I have. And I'm just setting it up so I have a bunch of white. So this is going to be, at this point, this is all just a bunch of white noise. Here, I'm going to take the cumulative sum to convert that white noise into the random walk. And to plot it, I'm going to use ggplot. I need to use the gather functions. So I need to keep track of where things came from originally. And then I'm going to go through and I'm going to plot it. And so here, each individual line is a line of a random walk. Now, I made a whole bunch of them to show you the overlap aspect to give you a better feel for the variance. What I really want you to notice is that as we go from left to right, the spread of those time series gets bigger and bigger and bigger. And you'll see that a lot of things are kind of like hovering around 0. The reason why is that things tend to average out. Like this one up here, this top time series, things are not averaging out yet on it, at least at this stage of the game. If we kept on running it, more than likely it would. But what's happening is that the random walk is going up, going up, going up, and eventually it'll start going down again, maybe a little bit up, down, up, down, down, down. There'll be a collections of ups and downs, so that in the long run, it's going to average out to be close to 0. Now, to show you the variance aspect that we talked about, you'll notice that here I plotted the variance of all those time series for each particular point of time. That's the blue. You can see it's kind of fluctuating. And the T, this is the theoretical, what I would expect to see of the variance on this particular example. And so we can see that it's hovering around where I expect it to be, which verifies the claims. All right, so now something as of interest to us is the autocorrelation function. So if I want to get the autocorrelation of a time series, I want the correlation of the time series with itself at 2 separate points in time. What I'm going to do is, just like regular correlation, I'm going to take the covariance up top, then I'm going to take the square root of the 2 variances and do some division. Boom, I've got the correlation. It's autocorrelation because it is the correlation of the time series with itself. Now, Cauchy-Schwarz inequality shows that autocorrelation is always between -1 and 1. I think almost everybody knows this at this point. Now, if the correlation is equal to plus or minus 1, then I can represent one of the 2 points in time as a linear function on the other. And the sign of the correlation equals the sign of this coefficient. Now the cross-covariance function, now here what we're interested in looking at is when I have 2 different time series and I'm interested in the covariance between 2 different times. So I have 2 time series, x and y, and I'm interested at time s for x, time t for y, and then it's just going to be the covariance just like you would naturally define it. And it is called the cross-covariance function because I have 2 separate time series. And the cross-correlation is defined similarly, that I take the covariance up top and then divide by the square root of the 2 variances. Now we can go a little bit further with this, and then we can look at multivariate time series. So with multivariate time series, we have a vector of values for each point of time. And so here for the example we're looking at is that we have our different components. You'll notice that this is a vector, and all of the sub time series are at the same time, and we have our components. And of course, I could check the covariance of the multivariate time series by selecting a component in time, 2 components, 2 times that I'm interested in. And very naturally, we can compute the covariance or correlation along time, or the components of interest, or both. All right, well, that's all I've got for you. Take care and goodbye.